So my name is Alf Coles. I am a professor of mathematics education at the University of Bristol in the UK. My background, before I came to the university, I worked in secondary schools in the UK for 15 years and was involved in practitioner research during that time. And so my interests and what I really want to talk about are questions arising from the teaching and learning of mathematics in schools. That's really where I'm interested. And the book that I'm going to be talking a bit about is particularly focused on primary schools in terms of the examples, but I think the issues that we raise are relevant across all phases of education. Now, I have got lots of tasks. Well, I've got 3 tasks for you at least to do in this next hour. And I want to try and find a way of getting feedback. So what I want to talk about today are 2 myths of learning mathematics and why you might want to rethink them. And this title has really come out of this book, which I wrote with Professor Natalie Sinclair. And I believe you are seeing Natalie next week. So quite a nice little pairing. I'm not particularly here to be a salesperson for this book, but I will let you know that Bloomsbury are doing a sale. I think there's up to 40% off this month. So that's maybe just a happy coincidence in case you did want to buy it. Okay, so in the book, we actually don't use the word myths, which I used in the title. We use the word dogmas. And part of the reason there is we're not particularly wanting to say these are all bad. So we're not particularly wanting to say these are ideas we just have to scrap. Rather, we're wanting to say these are ideas which have a history, that they have come out of particular contexts and perhaps have been very helpful ideas in some contexts and continue to be useful in some places, but that these ideas have, in the context where Natalie and I work, have become unquestioned. So they have become ideas which we notice with our colleagues and in schools, that these ideas have somehow become ideas that everybody agrees with, and the ideas that seem to be leading to some, for us, quite negative consequences. So in this session, I'm going to be talking about the first 2 of the dogmas on this list. Maths is a building block subject, and maths is hard because it is abstract. And Natalie is going to be talking about 2 others next week. I know she's taking the Maths is Culture Free. I actually can't remember which of the other 2 she's taking. Okay, so let's jump straight into it then. So this idea that maths is a building block subject. And what I want to do first is trace a little bit of the roots of this idea, because as I said, with each of these dogmas, we think there is something that is of value in the idea. We're not wanting to reject the idea, but we're wanting to try and think in maybe a bit of a more complex way about it. And it is obvious that mathematics can be laid out in a logical manner, in a building block kind of manner, building up from simple to complex. So when Natalie and I use the image of building block, we're really talking about this kind of logical development from simple to complex. And as I'm sure many or all of you on this call know, that there are very ancient roots to this idea of laying mathematics out in a logical format. And if we go back to Euclid and Euclid's Elements from around 500 BC, we can see that was a book that, again, I imagine some people here are more expert in this than me, but from what I understand, Euclid traveled around Greece and the known world of his time and gathered together all of the mathematical theorems and ideas that he could find, and he laid them out in this incredibly powerful way, starting from axioms, so starting from the simplest of assumptions, establishing one initial theorem or idea, and then building from there. And at each step, using what's just been proved as part of this sort of building block image. So maybe a little bit like a tree where it builds up from a solid root and then branches off, but you're always looking back to this this origin. This has obviously been an incredibly influential idea. Euclid's book was, I think, has been the most published book in English apart from the Bible. It influenced the English education system up until the 1950s. It was still studied in England until the 1950s, from several hundred years before then. And I think we still see it today in practices of mathematics education. And perhaps if you look at how mathematics as a subject is laid out, I think you can also see the influence of this idea that mathematical theorems usually proceed from axioms and then build up to the proof. But, and this is the key point, and I put it there, just because this is the order in which maths is often presented when it's written down, Natalie and I want to question whether this means it's the best order in which to learn it. And in fact, what we'll be suggesting quite strongly is, even though we can lay mathematics out in this logical way, we want to argue that's actually not a very efficient or very sensible way in which to order the learning of mathematics. So that may seem like a ridiculous idea, or may seem like a crazy idea to you, I don't know, or may seem very familiar to you. But I've got a couple of tasks now which I want to engage you in, which I hope will give you a sense of what alternatives might be to presenting learning in a logical sequence. Okay, so this is where you have to start doing something. So you will need a pen and paper, please. So I'd invite you to get a pen and paper. And I want you to draw a right-angled triangle on your paper. Yeah, draw a right-angled triangle. I'll just give you a moment to do that. Maybe you're getting resources to do that. Okay, and for this task, I'm only going to allow you to use precise copies of that triangle. So you're now going to only use the shape you've just drawn. So using copies of that triangle, you can make as many copies as you want. I want you to make a bigger version of your original triangle. So one that's maybe twice as long and twice as high, or 3 times as long, 3 times as high. But you've got to use copies of your triangle to make a bigger version. So have a go at doing that now. We'll check whether the task, if the task does not make sense, please feel free to unmute and ask me. Okay, and now see if you can make another bigger one and another. So you may have made a triangle that's twice as long and twice as high. Can you make one 3 times as long, 3 times as high, 4 times as long, but only using copies of your original triangle? And I'm interested in what you notice and anything you might be able to predict. So I'll give you a minute to just think about that and work on that. And then I'm hoping somebody might be brave enough to put their hand up and offer me something about what they've noticed. And just to illustrate what I hope is going on, you've got your original triangle, and then you're putting copies of that triangle together to make a bigger triangle. And then maybe you're doing that again to try and make a bigger triangle again. And I'm interested in what you notice, what you could predict if you keep on going. So I'll shut up for 1 minute while you do that, and then I hope one of you will be happy to talk. Okay, anybody willing to say anything they've noticed from doing this? Maybe anything about the numbers of triangles you were using? So maybe you'll feel brave to put your hand up. I don't know whether I can see if you're putting your hand up. If you are putting your hand up, please just unmute now and see. I can't see your screens now in this mode.
Fortunately, I can see the hands. Ricardo
perfect.
was the first.
Thank you. Has anybody put their hand up, Barbara?
Ricardo?
Great, thank you.
Yes, thank you. Do you hear me?
Yes.
So, maybe I can also activate the webcam, but I don't know if you will be able to see my drawing. But it was exactly the same as the one that Alf showed, just on the other way.
Beautiful.
So, well, I noticed that for every time that we enlarge this triangle, the total number of triangles or smaller triangles the original triangle that we used should be an odd number, but then now I would have to. But every time this number goes up by 2. Every time we need to add 2 triangle to the original. No, I'm explaining it in a very bad way. I'm aware of that.
No, that's great. Yeah. I think I understand what you're saying. So we had 1 in the first one.
Yeah.
4.
So we need
in the
to add another one, and then we need two more. So
yes.
we have.
Yes. So we've added from the first to the second. We've added 3, and then after that we have to add 5.
5.
So,
yes.
So we're adding 2
that's
more.
what I meant. Yes. So the total number is actually even.
It's fine. Yeah. Beautiful. No, thank you so much. Yes, great.
Another comment would come from a person whose name I cannot read. I don't know how.
You can call me Bea, actually. You can call me Bea.
Bea, okay.
Yeah, it's easier. Yeah, I noticed this same as Ricardo. Maybe you can see this, I'm not sure.
Yes, beautiful.
Yeah. And I was trying also to do some other shapes, and I got into trouble with my triangle.
Thank you, Bea. Okay, that's lovely. Really beautiful ideas there of what you've been noticing.
Isn't it a square number also? I mean, we had 1 triangle, then 4, then 9. So I'm now just hypothesizing because I didn't get the time to draw more, but maybe
beautiful.
Maybe it would continue with the square numbers.
So maybe they're square numbers. Beautiful, beautiful. Thank you, Catherine. Yes, you had a hand up. You may need to unmute. You're still on mute, I think, Catherine.
Yeah, hi. Sorry, I'm at King's College in London, Alf, which is where Natalie was. I can see, as well as spotting square numbers, I can see rectangles and parallelograms, which I like. And I was beginning to think about, is there a sequence in those as well?
So can you say a bit more? Where's your parallelogram and where's your rectangle?
Right, the parallelograms are going diagonally down the hypotenuse. Yeah.
Okay.
Does that make sense? Yeah. Whereas the rectangles are forming a sort of set of steps.
Beautiful.
I'm on tiny paper.
Yeah, lovely.
Steps below the first one. Yeah.
Really lovely.
So I've got some reflections as well, rather than just translations.
Beautiful.
Reflections,
Beautiful.
rotation, yeah.
Okay, thank you so much, everybody. That's really lovely to hear what you're doing. So one of the things I want to suggest you're doing here is that what you're telling me, so when you say, for instance, that these are square numbers, so this is perhaps not so. I think Catherine's taking us into another really interesting area about more of the geometry of it, but just staying with the number aspect. So when you're saying there are four copies of the triangle here, and there are 9 here, and so the increase is going up 2 each time. What you're telling me about is the area of this shape. So you're telling me that this shape has an area of 4 triangles, and this shape has an area of 9 triangles. And that indeed seems to be quite a kind of natural thing to notice, that when I've done this task with other people, that often people are drawn to this idea of how many. So if we pause for a second to think of what you've done here, my task was one where I asked you basically to enlarge your shape. So my task here was to take a shape and use copies of it to make a bigger version. So I'm asking you to make an enlargement. Bia was maybe going off into another very interesting area, looking at different shapes you could make with it. But staying with the original task, these are enlargements. So what you've done here is, or what this task is illustrating, I hope, is that enlargement could be a context for learning about area. Now, I don't know about the Polish curriculum, but certainly in the UK, so in England, Wales, Scotland, Ireland, and in Canada, enlargement would come some way after learning about area, that children would learn about area first, and then they would learn about enlargement. And that seems to be, in a way, the much more logical way of doing it, right? It feels like you need area to understand enlargement. But I think what this activity illustrates is that might not be necessarily the order in which things have to be taught. That it seems to me the task I gave you is one that is accessible for quite young children, would get them doing enlargements, and as a result of doing enlargements, learning about area. So that's one example of how maths as a building block, it might be a more complex picture, or at least that there are some choices around what I might do as a teacher in terms of how I structure the curriculum. Okay, a second task. Now, I really need to be in the room with you to do this one. I'm not sure I'm brave enough or even capable enough to do this on Teams with you. Barbara, maybe you could tell me though, can you see my cursor? If I'm moving my cursor around the number 7, Barbara, can you see that?
Unfortunately, no.
You can't. No, there's no problem. Okay, so this is a chart that I used a lot in my teaching, and I was fortunate to be a consultant with the UK government on some professional development materials for teachers, primary teachers, and about the only thing I managed to do as a consultant was make sure this chart got in as many places in the materials as possible. How this chart can work is, as a teacher, you might have a stick, and I was hoping to show you with the cursor, but you might tap on a number and the whole class will chant back, will say back the number that you've tapped. So I might tap on the number 40 and the number 2, and the whole class would say back 42. I might tap on a number and get the class to say back to me the number that's 1 bigger. So I might tap 42 and the class have to chant back 43, or 1 smaller, or 10 bigger, or 10 smaller. And one of the things the chart makes available potentially is something about number structure. how adding on 1 has a similar kind of action. No matter what I've tapped on above, if I end up 562, adding on 1 is just going to be 563. There's a similar, you could almost see the action of tapping on these numbers and how they change. You can also use it powerfully to work on multiplying and dividing by powers of 10. So I might tap on a number and the class will chant back to me a number that's 10 times bigger, or 10 times smaller, or 100 times bigger, or 100 times smaller. And it was this idea of multiplying and dividing by powers of 10 that I used I worked with a teacher a few years ago in a primary classroom. And we were interested in what some grade 3 children might do with this chart if we got them multiplying and dividing by powers of 10. So the challenge we set, and we didn't actually have this version of the chart to begin with. We had a version where the 1, 2, 3, the ones row was at the bottom, and it went tens, hundreds, thousands, tens of thousands, and there were no decimals to begin with. In fact, the decimals were printed. This sheet was printed on the back of the poster, and that's a relevant bit of information for a moment. So we gave the class the challenge that to start on any number on this chart, go on a journey of multiplying and dividing by powers of 10 and get back to where you started. So here are 2 different students' examples of what they did. So the child on the left started on 500, divided by 10, multiplied by 100, divided by 10, got back to where they started and gave themselves a tick. One thing to say to start with is that the children started being interested in their own challenges. So the idea of how do you get back in one go emerged from the class. It was not an idea from the teacher. And on the right, you see a student multiplying by 10 4 times and then dividing by 10,000. So as a teacher, we had not introduced division by 10,000. We'd only done tens and hundreds. So there's an interesting element of almost like creativity here, perhaps, or certainly extending the work that we'd offered as teachers. And we were encouraging students to write down what they were noticing. I've noticed it's clever because if you divide by 10, you times by 10 to get back, the top one. Or the underneath one, I found out that I times twice, but I divided once. By timesing by 10 twice and dividing by 100 once. So children beginning to make connections between these processes of division and multiplication. And I mentioned that the students perhaps noticed this decimal bit of the chart, which we hadn't originally been using with them, and asked to see that and work with it. And here's a child working with the decimals, again, multiplying and dividing by powers of 10. And then at one point, the children said, well, on my journeys, I can only go up and down one row. So if I just go back to the chart itself, if you're multiplying and dividing by 10, you just stay in one column. You stay in one column. And the children said, well, we want to go across columns. So the teacher and I thought about that. We'd not planned that. And what we offered to the children was, if you want to get, say, from the 7 row column to the 2 column, then you have to go through the 1 column. So what we offer to them is for any column, you can divide by, say you're in the 6th column, you divide by 6 to get to the 1 column, and from there you can multiply to whichever one you want to go to. So there's from 200 to 100, I divide by 2 times by 7. And this 3,000 to 0.04 was one of the lowest attaining children in the school, in the class, who's done really some quite sophisticated mathematics, we believe, dividing by, in fact, they've gone down to the units row and then across. They've made a little copying error perhaps at the end, but still some very interesting mathematics going on there. Okay, so what these 2 examples I hope have offered is the idea that mathematics doesn't have to have this building block or tree-like structure where everything moves from simple to complex. To go back to the Gattegno chart for a moment, I think you see children exploring a whole range of ideas and really sometimes pushing themselves to be thinking about division by 1,000 and 10,000 at the same time, thinking about connections between 10 and multiplication, and division. And it feels like the learning has much more the idea of a mangrove forest than a single building block tree-like image. In a mangrove forest, there are lots of horizontal connections. There are bits underwater and that are connected, and bits above ground, and of course there are some logical structures still, but it's not as simple as that. It's a much more complex picture of what might be going on when you're learning. And in the book, Natalie and I were keen to offer these kind of visual, if you like, representations of what we're thinking about, how we might think differently about each dogma. Okay, so that's all I want to say about maths as a building block subject for now. I think I'm going to keep going. We could pause for questions now, but I think I'll keep going. If you've got any question about this one, please note it down, and there'll be half an hour at least for questions at the end. Okay, so maths is hard because it's abstract. This is another of our dogmas. And as with the building block, I want to first of all retrace some of the historical ideas of this thought. And Natalie and I trace this idea really to Piaget. There are probably earlier roots to the idea as well, but I think Piaget seems a very very powerful source of this idea that abstract thinking is hard, and maths is abstract, therefore maths is hard. Piaget did some incredibly powerful and important work, of course, but work I think we perhaps all have come to question a bit, and for Natalie and I particularly, what we want to question is this idea that abstract thinking is somehow a late achievement in childhood. That the formal operation stage is from age 11 plus, or and so on. I mean, I think we know that the evidence of that claim is largely discredited. A lot of his experiments have been redone and shown to have quite different results. But I want to point to an example that is from a man called Caleb Gattegno, who worked with Piaget. He was Piaget's first translator into English, and so again has great respect for Piaget's work. But one example Gattegno used to really try and illustrate that Piaget's interpretations were not the whole story was that Gattegno looked at the example of children learning their first language. Now, I don't know if this example makes sense in Polish, but I hope it will make sense me describing it in English. But in English, it's very common to hear young children around aged 3 to say something like, I runned. Now, in English, the correct grammar here would be I ran. Gattegno uses this example to make a number of points. And the first is he uses it to suggest that we do not learn language by imitation or by imitation alone, because a child is unlikely to have heard an adult saying, I runned. So if they've not picked up that word by imitation, then what else is going on? And Gattegno suggested that error shows the following capacities. It shows that child, aged 3, remember, has noticed a pattern and a rule. And the rule being that if I want to make something past tense, I put ed on the end of it. They've generalized that pattern. They've not heard someone do that with the verb I run, so they've generalized, and they've applied that generalization in a novel context. Well, these are the hallmarks of mathematical thinking. What is abstract thinking if it's not doing all of those things? And Gattegno proposed, and I find it a very convincing argument, that children aged 3 are doing that. And in fact, that's how we learn a language so powerfully as a young age, that we apply mathematical ideas, we apply algebraic ideas really to our learning of a language. So completely kind of turning on its head this idea that abstract thinking is something we can only get to in later life. So again, we want to suggest that this, a bit like the building block, might suggest some quite different ways of working with the curriculum than is typical. One way that the idea that maths is hard because it's abstract is used is the idea that we need to move from concrete to pictorial to abstract. And I don't know whether this is an idea that is around very much in Poland, but this is an idea that's very, very present in schools in England at this time. And Natalie and I want to suggest this is not the way learning has to proceed. And in fact, even in, say, Singapore, which is one of the origins of, or one place, not necessarily the origin, but one place where this idea is used a lot in the curriculum, the point is actually that as quickly as possible, you have all three of these ideas around, and learners are expected to make shifts between them. So although there is some sense of a movement, the key thing is trying to make relations across those ideas. Going back to Caleb Gattegno for a moment, one of his curriculum ideas, which links to this idea of where abstract ideas come from, is that Gattegno proposed that you think about number as a length in the early years curriculum. And this has a strong link to the ideas of Davidov, that some of you may be familiar with, the Russian educator who developed his own curriculum based on measure, a number as measure. So for Gattegno, it was specifically length. For Davidov, they wanted number as measure. So Gattegno developed what we call in England Cuisenaire rods, which are these wooden blocks, all with a 1 centimeter square cross section of different lengths and different colors. And Gattegno suggested that in working with early number, you give children a time just to play with these rods and see what patterns they make. And at some point, they might start comparing their lengths, and you might encourage them to compare lengths and to think about which rod is longer and which rod is smaller. And before any numbers are introduced, Gattegno would encourage children to be looking at these relations of greater than or less than. So that in itself is perhaps a reordering. That's not particularly a building block idea as we know it. We might think that you need to have numbers before you can do greater than, less than. Gattegno would suggest you can do that just looking at the attributes of length. And at some point, children might start making this kind of arrangement, where 2 of one rod matches up against the length of another rod. And this is the point at which Gattegno wanted to introduce number. So the first number he introduces in the curriculum is the number 2, not to represent the length of a rod, but to represent the relationship between 2 different kinds of rods. So in some ways, his first number is already abstract. It's not the length of a rod, that there is not a single rod there. You can't point to the 2 and say this is 2 in the diagram. The 2 is a relationship between one bit of the diagram and another. And what Gattegno does in his curriculum is the second number he introduces is actually the number 1/2, where he suggests with grade 1 children, you would then introduce the idea of fractions, with the red rod being half of the pink. And he would suggest, and his curriculum indicated, this is a very natural way of working for children and can be very successful. So again, linking to the building block idea that we don't have to follow mathematics in this logical way, and also linking to the idea that the difficulty of maths is not because it's abstract, that very young children can work with what I would see here as abstract relations on concrete objects. So you have a concrete object there, but what you're paying attention to are abstract relations between them, which allow you to consider both the 2 and the 1/2, 2 different sides of that relationship. Okay, I want to show you one actual classroom example of something which I see as quite similar going on. And this is, I've got the order wrong way around. Yes, this is, we'll go back to the imagining task if we've got time. And this is, I want to show you a little clip from the teaching of a man called Robert Davis. And I'm interested in you paying attention to what are the symbols representing in this video clip. So I'm going to share a different screen. It's quite an old video, I have to tell you. So it's all in black and white. So it's probably from 1962 or something like that. We don't know exactly the age of the children, but I think maybe they're around 6, I would judge, 6 or 7. I think the context is quite clear of what he does. He sets it up from the beginning. We're just going to watch 2 or 3 minutes. And I'm interested in you thinking about what are the symbols that he writes representing. Okay, so it'll just take me a second to share my screen again. This video, I should say, oh, no, sorry, I've not shared the sound yet. This video, I should say, comes from the Video Mosaic archive at Rutgers University. So if you're interested in that archive, it's an extraordinary archive. The website is called Video Mosaic, I think, .org. Robert Davis worked at Rutgers University, and there's now a Robert Davis Institute. And he developed, one of his big bits of research was something called the Madison Project. And again, you can find things online about the Madison Project. It was a project that went on for 25 years in the end, looking at children's computational thinking. Okay, so here's a clip of Robert Davis teaching. As I say, we're going to watch 2 or 3 minutes. What are the symbols representing? It's that old, so we have one of those things at the beginning.
Okay, Jeff is going to tell us when to start, and you say go.
Go.
Okay, Jeff said go. And I'm going to put 3 stones in the bag that Nora is holding. I'm going to put 3 stones in. Are there more stones in the bag now, or less than there were when Jeff said go? Charlotte, what do you say?
More.
More. And how many more, as if you didn't all know? How many more? Laurie, how many more?
3.
3 more, huh? Okay, and now I'll take some stones out of the bag. How many stones do you want me to take out of the bag? Barbara, how many stones will I take out?
3.
3, I'll take 3 out. Okay. Barbara says take 3 out, so I'll take 3 stones out. There's 1. There's 2. There's 3. Take 3 stones out. And I better write that. Took 3 stones out. Now, are there more stones in the bag than there were when Jeff said go, or are there less? Brett?
There's the same amount.
There's the same amount, and I bet that's right. And what will I say here, as if you didn't all know? What will I say?
Oh, yeah.
Sandy, what will I say?
0.
0.
Negative
Right.
0.
Okay, that was that time. I need 2 other assistants. Thank you very much.
Oh.
I need somebody to come hold the bag. Paul, will you come hold the bag? And I need somebody else to come and say when to start. Bruce, would you come? Okay. You're going to tell us when to start. Good.
Go.
Go. Bruce said go. How many stones do you want me to put in the bag? Nancy, how many?
5.
5. Okay, I'll see if I've got 5. Yep. Turns out I've got 5 stones here. I've got 5. Got 5 stones there. And so I'm going to put all 5 of these in the bag. And I'd better write that before I forget. Are there more stones in the bag than there were when Bruce said go, or are there less? Jeff?
More.
And how many more?
5.
5 more, huh? Okay, how many do you want me to take out? Nora, how many will I take out?
5.
I don't want to do that. Some other number.
6.
6? All right, I'll take 6 out.
Huh?
Can you open it up?
Did you have stones in the bag
Take.
to start with?
Take 6 out. I better have had, hadn't I? Won't be able to do this if I didn't. Let's see. 1, 2, 3, 4, 5, 6. That was more good luck than good management. I got exactly 6. Okay, I'll write it. Have I got more stones in the bag than I had when Bruce said go, or have I got less? Brett, what do you think?
Less.
Less. And anybody know how many less? Nora, how many less? 1 less, okay. And how will I write this 1 to show that it's 1 less? Gary, how will I write? Negative 1. And that's just what I'll do.
Okay. Right. Now I've got to try and get back to how I stopped sharing. Okay. Now, what I would normally want to do is spend time reconstructing what happened in that video, but we don't really have time to do that. So I hope it's okay to jump straight to the question of what were the symbols representing? And I wonder if anybody would like to offer something about what they thought the symbols were representing in that video. So please raise your hand or just unmute. Bia, are you're?
Yeah, I was just wondering what you mean by symbols.
The numbers. So sorry. So
Okay.
when he writes the 3 and the 5 and the 6. Yeah. But Harita, so thank you for the question. Yes, that's an important question. Harita, you had your hand up.
Is it like the signed quantities that is represented in as the answer?
Yes. So when he writes 3, I suppose my question is, what's that 3 representing? So they are signed quantities. That's definitely true. What the symbols are. What does it represent in the context of the problem, though, is my question.
More or less.
Okay. Yeah, interesting. Anybody like to add to that? So Harita said that the symbols are something about more or less, which is, I think, really interesting. Anybody like to offer anything building on that?
Yeah, I agree with Harita because he was adding, for instance, the 3, and we had no idea how many were in the bag before.
Yes.
So it's not like we know what was the quantity before we started the game, the go game, or the child said go.
Yes.
So it represents the change after the go.
Beautiful. I totally agree. And it took me a long time to understand, why was this child saying go? I didn't understand, why do you need, because the child seems to just say go and then not do anything else. But I think, Bia, there's something very subtle in what you've said there. It's representing the change after the go. So we needed this point in time to then be able to say it's change from that moment. Yes, I totally agree. So when it writes, so Bia, could you just follow that through? So when he writes 3 subtract 3 equals 0, could you just follow through what could you continue your interpretation? What's that actually meaning in this context?
Yeah, in this context, it would mean that after the go, they added 3 to the bag. And then he asks for a suggestion for a removal. And that's why he adds the minus. It's denoting the removal. And he asks also for how many to remove. And the number, the quantity of how many to remove is written after the negative sign. And then the equal sign denotes the result after having, after having performed both actions.
Beautiful. That's really lovely. Thank you so much. Flores, yes, you have a hand up, please.
Yes, good morning, everyone.
Good morning.
I think the children are speaking about stones. So the numbers are representing stones. So then at the last time, we have -1 stone. And then what means to have a minus stone? A negative stone? I don't know what is an abstraction, I think.
Okay, so this is lovely what you've just said, Flores. So I want to hold both Bia's and Flores' points there. Thank you very much, everybody, for sharing those ideas. And I want to offer to you how I see this video and what I think is going on here and why it's so powerful. Okay, so for me, the power of what's going on here. Sorry, I haven't got this. I meant to have this animated. The power of what's going on here seems to center around what gets symbolized, and I think I agree with Bia that what the symbols are doing is they are focusing on the actions with the stones or the change in the number of stones. So you're right, Flores, that -1 stone doesn't seem to make any sense. But I think why this activity seems to make sense is that the -1 is talking about a change in the number of stones. So it's not talking about there having to be -1 stone, but it's saying there's one less stone than there was to start with. So it's the action. If you like, the result of all my actions, the putting in and the taking out, the result of all that has been the equivalent of taking out 1 stone. So that equals maybe could be an equivalent, perhaps, is a simpler way of saying it. So a bit like the Gattegno with his 2.5 from the rods, what I observe here is a concrete situation where what gets symbolized is abstract from the very beginning. And I've certainly shown this video to primary teachers who cannot believe that children seem to be working with the negative in such a natural way. I mean, we don't see very much of them working, of course, do we? But I think you can imagine from that situation how you could develop some things for the children to do based on this situation where the negative would not really pose too much of a difficulty. So for me, this is showing how these really quite young children are handling confidently this abstract notion. And Natalie and I have written about the idea of a symbolically structured environment as one way of characterizing what's going on here in the Bob Davis work, also in the Gattegno work and with the work on the Gattegno tens chart. We see some similarities across those 3 examples I've given you here. I'm not going to go into that idea now, but if you're interested, there's bits in the book and we've written some articles about this idea of a symbolically structured environment. But a key for me is that what's happening here is that you are symbolizing an action or you're symbolizing a change. And I think what's powerful, what makes that powerful is that as humans, we know, young children know about doing and undoing things. So that seems to be just something which children very early on have an idea of. Gattegno would even say we're born with that sense that I do things and I can undo them. So if you symbolize an action or a change, it's quite straightforward to think about that change or action happening backwards. We can undo it. And so you then have another symbol that can be linked for the action or the change in reverse. So for Gattegno, he had his 2.5. For Bob Davis, he had his positive numbers, the 0 or the positives, and he had the negative. But because their change, because their action, the 2 symbols can arise together. And these things which we're told or we know in a standard curriculum, these symbols that make real difficulties for students, the fractions and the negatives, we have examples here, I think, where they can arise quite naturally with the integer numbers. So in other words, if we don't get caught up in the idea that maths is a building block, if we don't get caught up in the idea that it's hard because it's abstract, we might find some curriculum orders, some curriculum reorderings, which make some of the problems which we've suffered in maths education for decades, might make these problems just not arise in the first place. Maybe there doesn't need to be a big issue about children's understanding of fractions if we can introduce the symbols in a different way. Maybe negatives doesn't have to be this big thing that lots of children get confused about if we introduce the symbols in a different way. And what Natalie and I have for this dogma is the idea that the sort of hard to abstract is this kind of arrow thinking, that there's just one way to go. Our thinking has to proceed simple to complex in this way that we've always done, but that actually there may be different routes and slightly different endpoints for learning. I wonder if we've got time for that. I did have one third task. I'm going to offer you, I am going to go back to this third task, but we're going to do it very briefly, but I'm not really going to have time to get feedback from it. But I want to also offer one other type of activity, which for me is also about how abstract thinking doesn't have to be hard. And these are activities using our mental imagination. So I'm going to ask you to picture some things in your mind now. So you may want to picture it as like a computer screen. It may, these images, I'm going to ask you to evoke some images. Maybe they happen on a screen for you. It might be you can't actually see them at all, but you maybe just get a sense of them. You can feel these images and still answer things from there. You might want to shut your eyes to do this, and I'd invite you to do this without any drawings. So just try and do this picturing what I'm saying in your mind. Okay. I'd like you to imagine a number line. And I'd like you to try and visualize it, picture it as vividly as you can. And the line is horizontal. And I would like the negatives on the left and the positives on the right, so that a number line increases as you move from left to right. And place the 0 somewhere in the middle of your mental screen or your mental image. And I want you to color that number line red. So it's going to be a red number line. And I now want you to introduce a blue number line, and this blue number line is going to move. The red one is going to stay fixed. The blue one's going to move. So to begin with, I want you to match the blue number line precisely on the top of the red one. So they match exactly. And now I want you to move the blue number line 3 spaces to the right. And where does the number 6 on the blue number line end up? See if you can see that. Where does the number 6 on the blue number line end up? If we had a chat, I'd want to get some feedback. In a classroom, I'd want to get some feedback. I'm just going to go through this much more quickly than you'd ever do in a classroom. So you could just imagine you'd pause and discuss in a classroom as long as you might need. But I'm just going to go through just three iterations of this to give you a sense of some possibilities. So I think I asked, where does the 6 on the blue line end up? And I think I'm right in saying my one ends up on 9 on the red. So I don't know whether that would have happened for you too. Okay, pick the blue number line up again now and place it back again exactly where the red one is. And now I want you to reflect the blue number line. Or no, maybe I want you to rotate it. Sorry, no, I want you to rotate it 180 degrees. Has the same effect. Rotate the blue number line 180 degrees. And where does 6 on the blue number line end up now? So where does 6 on the blue number line end up? And I hope you would agree with me that that ends up as -6 on the red number line. Okay, again, in a classroom, we might spend time doing more of those. Reset again. So now the blue number line again fits exactly over the red one. And now I want you to move the blue number line 3 spaces to the right. And then I want you to rotate it around 0. Sorry, I hope I said rotate around 0 before. I meant to. So move the blue number line 3 spaces to the right and then rotate around 0. And my question now is, where does 6 on the blue number line up?
At -3.
Oh, wonderful. Did anybody get a different answer? Did anybody get a different answer? I like the -3. I think I can see that. Does anybody get a different answer though? Because I can see a different possibility as well. So, and again, we haven't got time to go into this in detail, but I think there's a question because in fact, I was deliberately ambiguous about which 0 we rotate about. So I think we can get -3 rotating about one of the zeros. If we rotate about the different 0, if we're 0 on the red line, then you might think about where would that end up. Anyway, we don't have to go there because I'm almost at the hour. But it can be quite nice in a classroom actually when you get these different ideas. And what answer did you get?
A -9.
-9. I think that's what I get as well. Yes. Yeah. So we might get -3. We might get -9, and there are some nice discussions that can happen in a classroom from that. So I want to offer this as another image of abstract thinking that I would say is accessible to very young children. And I would also want to argue that developing children's capacity for mental imagination is actually a very important part of learning mathematics, and again, from a very, very young age. So even things like the Gatenio chart are things that you might, where was the Gatenio chart? That you might do physically, but you might at some point get children to try and do work on this, picturing the chart in their mind. That seems a very powerful thing to do. And we've been doing the number line, which again is a powerful tool that at some point for children to be able to work with it mentally. I'm going to ask Bia this in 1 year's time. Next time I see Bia at a conference, I'm going to ask her, what does she remember from this talk? And my conjecture is that maybe the thing she might remember is the number line rotations, because there's something which I don't think is very well understood in psychology. There is something incredibly memorable about evoking your own mental images. It seems you don't have to pay much energy to remember these things, that they somehow, we retain them in our mind in a quite extraordinary way. Okay, Barbara will be wanting me to close up because it's 4 o'clock on my time, I think 5 o'clock for you. So here are some takeaways. So yes, so this image of different routes, different endpoints. So some takeaways. Sometimes if a student is stuck, I believe they may need something more complex or more abstract, not less, in order to make progress. In England, we have the situation where when children start to not succeed in maths, they get taught the same content again and again and again. And particularly when they get to secondary school, maybe they'll essentially have the same curriculum for 5 years. They keep getting taught about number and percentage, and they keep failing on it. This idea only comes, you'd only do that if you think maths is this tree-like structure, and so there's something missing, and so we have to keep doing that because they can't possibly learn anything else if they don't have this missing link filled in. I don't think there's any evidence that that's the case. In fact, sometimes being offered a kind of big picture, I think the Gatenio chart is one thing that does that. I think, the Gatenio fractions and number at the same time, the Bob Davis negatives and positives at the same time. Sometimes being offered a big picture can be both energizing and also help make sense of content that can otherwise appear atomized and difficult to understand. So sometimes I think you need this more complex picture to make sense of things. One thing that I think that means is that we need to rethink some curriculum orders, such as doing area before enlargement. The idea of numbers I didn't particularly go into this time, but in English, the numbers 11 to 19, the number names for those are very irregular, and the number system is very regular after 20. So one proposal that I made that I'm pleased to say is now part of English advice to teachers in primary schools is that you should teach the numbers 20 to 99 before you go back and teach 11 to 19. Because by teaching these bigger ones in an English language context, you're teaching the system, you're teaching the structure. And once you've understood the structure, then you can go back and learn about the irregular ones from 11 to 19. And so just more broadly, because a student has not understood one thing, for me, it feels very important that they're not denied access to learning more complex or abstract things as a result of that. If I think about my own children who have some problems with dyslexia, for instance, they find algebra much more straightforward than number. And none of my children know their times tables. If they were not allowed access to the curriculum because of that, you know, I don't think they would have ever learned their times tables because it's just difficult for them. But actually, it doesn't mean that they can't learn algebra. And I do believe mental imagination work is one mechanism in which to work with complexity and abstraction in a manner that's highly memorable. And I think there's a lot of research, and it links actually to Bia's work on silent videos. I think that there's a lot of research that could be done in this area. Thank you very much, everybody, for your engagement and participation. I hope it's okay that there was a bit of participation, so I hope it was okay to go slightly over the hour. There's the book again, if you are interested after this, but I'm going to stop, and I hope there will be some time now for questions and comments. I'd be very interested to hear any reactions. Thank you, everybody.